The Hall effect. The Hall effect comes into play when we insert a thick plate into a circuit along with the battery and wires. FYI, one use for the Hall effect is to quantify the number of charge carriers N for a given metal. Anyway, the Hall effect is the one case we might run into where our focus on conventional charge flow and its associated right-hand rules breaks down. With the Hall effect, we must focus on the motion of the conduction electrons, and thus we must use some variation of the left-hand rule, which is what you always use for negative charges. This figure here shows a circuit, and it has a battery in it. It's got two wires, and it's got a thick metal plate. And in the vicinity of the metal plate, there's a magnetic field that's directed out of the page. We can tell that because the magnetic field is represented by dots. Let's show the direction of conventional charge flow, and I'm going to label it I positive. Conventional charge flow would be in this direction, and I'm going to label it I with a little subscript plus there. That's conventional charge. The conduction electrons actually flow this way. I might label those with I with a little negative subscript there. Now, let's focus on the flow of charge through the thick plate. Let me recopy the flow of conventional charge, which would go in that direction, and the conduction electrons, however, would tend to flow in that direction. Use a right-hand rule to determine the direction in which positive charges in the plate would tend to drift due to the magnetic force on them. The conventional charge would, through the plate, be going down towards the bottom of the page. And according to the right-hand rule here, when positive charges are moving down towards the bottom of the page and the magnetic field, check out the nails, are coming towards you, look at the very top of the screen, you can see that the force is directed to the left. Use a left-hand rule to determine the direction in which negative charges in the plate would tend to drift due to the magnetic force on them. Here come our conduction electrons, and to figure out what direction the magnetic force acts on those, we need a left-hand rule. So we got to have our left thumb. And through the plate, they're going to be going towards the top of the page. The magnetic field is directed towards us. So in what direction is the force? Right at the bottom of the screen, you see that little arrow right there where my finger's tapping. To the left. Uh-oh, everything scoots to the left, according to what we've just circled. Now, which of these scenarios can actually happen? Is it the conventional charges that could scoot to the left, or is it the conduction electrons that could scoot to the left in this thick plate? And it's the conduction electrons, because those positive charges, the nuclei of the atoms, they can't really scoot much, but some conduction electrons can. It's actually part C here that really happens whenever we have this thick plate. Therefore, a buildup of what charge will appear on the left edge of the plate, negative, and a buildup of positive charge will appear on the right edge. Let's draw some negative and positive signs along the edges. Along the left edge, we're going to have some negative charge buildup, and on the right side, we're going to have some positive charge buildup. Should be the same number of those, kind of like so. Which means we're going to have a higher potential on one side of this thick plate and a lower potential on the other side of the plate. This side here is going to have the higher potential, and this side over here is going to have the lower potential. Often whenever I write a V, I'll write a V with little hooks there on the top to indicate that that's a capital V. Let's finish up then by answering part I here. To determine the charge carrier density N of the metal out of which the plate is made, we said that one application of the Hall effect is to help us figure out what the charge carrier density is for a given metal, zinc, copper, aluminum, whatever. We'd need to measure the following: the dimensions of the metal plate using a meter stick or a vernier caliper, if you've ever used one of those, the strength of the magnetic field, the difference in potential that we mentioned earlier and the current. We would also need to look up or know the charge on an electron, but of course, that's a constant and has already been determined and is well known. To measure the magnetic field, we would use a device called a magnetometer. To measure delta V, we would use a voltmeter. And to measure I, we would use an ammeter. It's a little thing, but don't ever call a voltmeter a voltometer. My students know that if they really want to get under my skin, they'll say, Mr. Bergman, should we use a voltometer here? Oh, you go out in the hall. Okay. And don't call an ammeter an ammeter. It's not an ammeter, it's an ammeter. All right, there you go. That's the Hall effect.